Okay, let's start with the vision. Imagine if you could, store the entire history of the internet, every single thing, on a device smaller than a paperback book. I mean, we're talking about capacity that makes today's storage look, well, kind of ancient.
Yeah, that sounds like total science fiction, doesn't it? But, for years, engineers have been in this really tough battle with physics to get there. The future of data storage, like for the whole world, it really hit a hard physical wall. And the solution, kind of surprisingly, wasn't some bigger magnet or a brand new material. It actually involved hitting that wall with a tiny, super powerful laser beam.
And that's the tech we're diving into today. Welcome back to the Deep Dive. We are getting into heat-assisted magnetic recording, or HAR. It's fundamentally changing how we store digital information.
Right. So our dope dive today, it's based on a whole stack of recent technical reports that detail this huge shift. Our mission, basically, is to cut through the technical jargon, really understand the core physics. How does that laser actually give us these massive storage gains? And ultimately, what does this all mean for things like reliability and the cost of all the cloud services you use every day?
Because, let's be real, for the last decade or so, we've been stuck, right? Conventional hard drives, the ones storing most of the world's data, they rely on something called perpendicular magnetic recording, PMR.
And PMR, well, it hit a fundamental limit. It's called the superparamagnetic limit. Think of your data bits, like the ones and zeros, as tiny, tiny magnets. To pack more data in, you have to shrink those magnets down.
Smaller magnets, more data in the same space. Makes sense.
Exactly. But there's a catch. The limit was around 1.3 terabits per square inch, if you go smaller than that. Those tiny magnets become thermally unstable. Just the normal heat around them can actually make them flip their magnetic direction.
Oh, wow. So just ambient temperature could corrupt your data.
Bingo. Data corruption. It's a huge problem. You can't reliably store information if the bits might just randomly flip on their own.
Okay, so that's the wall you mentioned. Game over for just shrinking things further with PMR.
Pretty much, yeah. But before we jump to the fix, HAMR, it's worth taking a second to appreciate just how amazing even current hard drives are. The engineering is just incredible.
Totally. Even these PMR drives, they store data using those tiny magnetic domains oriented vertically, right? Using materials like cobalt, chromium, platinum alloys.
That's right. And the precision needed to read and write that data, it's almost unbelievable.
You're talking about the read-write head flying just nanometers above the spinning platter, like incredibly close. How close are we talking? Is there a good analogy?
There is one, and it always blows my mind. Imagine a Boeing 747, a huge plane, flying at Mach 800, super fast.
Okay.
Now imagine it flying less than 1 centimeter, like half an inch off the ground. And while doing that, it's counting individual blades of grass. That's the kind of scale and precision we're talking about with the read-write head. And that gap is maintained just by airflow.
That's actually nuts, so it never touches down.
Never touches. And when that head reads the data, it's using quantum mechanics. Things like giant magnetoresistance, GMR, or tunneling magnetoresistance, TMR.
Quantum effects.
Seriously. Yep. It's a quantum trick that lets the head detect those super weak magnetic fields from the tiny bits without physically contacting the disk.
Okay, so reading is this incredibly precise quantum dance. But you said the problem was writing the data, right?
Exactly. Reading was fine, but writing hit the wall. To get past that 1.3 T-bin density limit, engineers realized they needed materials that were magnetically tougher, ones with higher magnetic stability, or what we call higher coercivity.
Coercivity. So that just means the material is harder to magnetize or demagnetize. It holds its magnetic state better.
Precisely. If you make the magnetic bits, the domains, smaller, they need to be magnetically tougher, higher coercivity, to resist flipping from heat or stray fields. But here's the kicker. The right head, that little electromagnet flying over the surface, it just couldn't generate a magnetic field strong enough to actually flip those super tough, high coercivity magnetic bits. At least, not at room temperature.
Okay. So we found materials stable enough for tiny bits, but then couldn't actually write to them with the existing heads. A classic catch-22.
Exactly. The magnetic force just wasn't enough. So if you can't make the magnet stronger, what do?
You cheat. Use something else.
You use heat. And that brings us to AMR, heat-assisted magnetic recording, the fire solution, basically.
The fire solution, I like it.
Yeah.
So AMR is the breakthrough.
It really is. And it's funny, the basic idea was actually thought up way back in the 1950s.
The 50s. Seriously.
Yeah, but making it work at the nanoscale, with the precision needed, that took decades of engineering. It only really became commercially viable, like, now.
Yeah.
2024, Seagate's really leading the charge with their 28, now 30 terabyte drives.
30 terabytes on a single drive. Okay, so how does the heat actually assist the recording? What's the science there?
It cleverly uses the fact that a material's magnetic toughness, its coercivity, isn't constant. It changes with temperature. When you heat a magnetic material close to a specific point called its Curie temperature, its coercivity drops dramatically. It suddenly becomes much, much easier to magnetize.
Yeah, as you heat up just the tiny spot you want to write to,
Yeah.
it becomes temporarily soft magnetically. The existing write head can easily flip its magnetic direction, and
And
then
then it cools down almost instantly, locking in that new magnetic direction. The coercivity shoots back up, making the bit stable again at room temperature.
okay, but wait, you mentioned heat. How hot are we talking? And
Yeah.
how do you heat just one tiny spot without messing up the bits next to it? That seems like a huge challenge.
It is a huge challenge. We're talking about heating a spot to roughly 400 degrees Celsius.
400 C, that's what, 750 Fahrenheit? On a delicate hard drive platter?
Yep, sounds crazy, right? But the key is precision and speed. A tiny laser diode is built right into the recording head assembly. It travels with the head, it shoots a minuscule pulse of light, heating that nanoscale spot to 400 degrees C. But critically, this entire heating and cooling cycle happens in nanoseconds, billionths of a second.
Nanoseconds, wow. So it heats, writes, and cools before the heat can spread sideways and erase the neighbors.
That's the genius of it. The heat is incredibly localized and incredibly brief. The spot cools down so fast the adjacent data is perfectly safe.
Okay, that makes sense. And the material itself must be special too, right? Not the old cobalt alloy.
Absolutely not. You need something that can handle this extreme thermal cycling and has that high coercivity at room temp. HAMR drives use these advanced materials, usually iron platinum alloys, specifically FEP'd, often with some carbon added. FEPC granular films.
Iron platinum.
Yeah.
These materials have what's called high magnetic anisotropy. Basically, they're rock-solid stable magnetically at room temperature, which is exactly what you need to beat that super paramagnetic limit. But crucially, they also have that property where their coercivity plummets when you heat them near their Curie point. They become momentarily writable.
So the head flies over, the laser zaps the spot for a nanosecond, softening it up. The magnetic field from the head flips the bit,
Right.
and bam, it cools instantly, locking the data in place, nice and stable.
You got it. That's the core mechanism. But there's one component in this whole system that was and still is the absolute hardest part to engineer. The real Achilles heel.
Let me guess. The laser part, delivering that heat precisely.
You're warm. It's the component that focuses the laser light. It's called the near field transducer, or NFT.
NFT. Okay, I've seen that acronym mentioned a lot in the reports. Why is the NFT so tricky?
Because it has to do something that seems physically impossible. It has
Yeah.
to take the laser light and concentrate it down to a spot smaller than the wavelength of the light itself.
Wait, how? Doesn't physics say you can't focus light smaller than its wavelength? The diffraction limit.
Normally, yes. But the NFT uses a trick involving something called surface plasmons. It's essentially a nanoscale antenna, a tiny piece of metal shaped just right. It converts the light energy into these surface plasmons, which are like waves of electrons on the metal surface, and those can be confined to a much smaller area, well below the diffraction limit.
Okay, that's some serious physics magic right there. A nanoscale antenna for light.
It really is. Think of it like a funnel, squeezing that laser energy down onto that tiny, maybe 30 nanometer wide spot on the disk.
That concentration of energy must be intense.
Unbelievably intense. The NFT delivers about 100 microwatts of power, which doesn't sound like much, but concentrated onto that tiny spot. It creates light intensities roughly 100 million times greater than direct sunlight.
100 million times. Okay, now I see the problem. How does this tiny component, this NFT, survive that kind of intensity, plus being heated to 400 Celsius over and over, thousands of times a second, for years?
That is the question. Reliability. It's the major hurdle, and we'll definitely circle back to that trade-off. But first, let's talk about the payoff, because despite the difficulty, the results are huge.
Right, the whole reason for doing this. So PMR topped out around 1.3 terabits per square inch. Where does HMR take us right now?
Immediately, commercially available drives are hitting 2.5 to 3 terabits per square inch, double or more the density.
Wow, double the density almost overnight.
Yeah, and that directly translates to the 30 TB drives you can buy today. But the roadmaps, the plans from manufacturers like Seagate, they clearly show 50 TB drives coming soon. And there's a pretty clear line of sight, based on the physics, to hitting 100 TB drives by maybe 2030.
100 terabytes
Yeah.
in a standard 3.5-inch hard drive. Okay, that definitely explains why hard drives aren't disappearing anytime soon. Flash storage is great, but for sheer capacity per dollar, this keeps hard drives way ahead for bulk storage.
Absolutely. And it's not just about capacity either. There are other performance benefits. Things like sequential transfer speeds, reading or writing big files have nearly doubled, up to maybe 275 megabytes per second now. And overall input-output operations per second, IOPS, which matters for random access, that's improved too because the writing process is so precise.
Okay, better speed, much higher capacity. Now here's the bit I found really surprising in the research. You'd think adding a laser constantly heating spots to 750 Fahrenheit would use more power, right?
Intuitively, yeah.
But the reports say HAM drives are actually more energy efficient. How does that work?
It seems counterintuitive, but it comes down to efficiency per terabyte stored. The HAMR components themselves, the laser, the NFT, they do add a little bit to the power draw of a single drive, but because you're storing so much more data on each drive, double or more, you need fewer physical drives to store the same total amount of data.
Ah, okay. So for a big data center needing, say, a petabyte of storage, they can use maybe half as many HAMR drives compared to PMR drives.
Exactly. And fewer drives means less power for spinning disks, moving heads, cooling, everything. The net result, about 70% lower power consumption per terabyte stored.
70% lower power per terabyte. That's huge for sustainability and operating costs for data centers.
Massive. It's a really significant environmental and economic benefit.
So Seagate is shipping these drives. Is the rest of the industry jumping on board? Is it officially the future, or are there competing ideas still?
Well, that's the other big indicator. It really looks like AMR is becoming the consensus standard for the future. You've got major cloud players like Google who've already gone through the long process of qualifying these drives for their massive data centers. That's a huge vote of confidence.
Okay, if Google's using them.
Right. And maybe even more telling, Western Digital, the other big hard drive manufacturer, they initially backed a different horse, a technology called MAMR, microwave-assisted magnetic recording.
Microwaves instead of heat.
Yeah. But recently, WD announced they're also shifting their future high-density plans to HAMR. When your main competitor essentially says, okay, you guys were right, that suggests the industry is aligning. Thermal assistance won the density war, it seems.
All right, so AMR is the way forward, but let's go back to that Achilles heel you mentioned, the NFT, that tiny antenna dealing with insane heat and light intensity. How big of a reliability problem is it?
It's still the primary technical challenge, no doubt about it. NFT degradation, that extreme thermal cycling, heating up and cooling down thousands of times a second, it causes physical stress, structural deformation over time.
So the NFT itself can just wear out, break down.
Essentially, yes. Research clearly shows the lifetime of the NFT decreases exponentially as the operating temperature goes up.
Exponentially. That's a scary curve.
It really is. It creates this fundamental trade-off. Engineers are constantly juggling. You want higher performance, maybe faster writing, which might mean pushing the laser power or duration slightly, but that increases the temperature stress on the NFT, potentially shortening its lifespan, and thus the drive's overall reliability, performance versus longevity.
So is most of the current research focused on just making that NFT tougher, more resilient?
A huge amount of it, yes. It's less about finding new ways to increase density right now and more about optimizing what we have for long-term use. That means materials science finding even better FEPT alloys or related materials that are inherently more stable at high temps. And it means optical and thermal engineering designing more advanced NFTs that are maybe more efficient at focusing light or better at dissipating their own heat, reducing that self-heating effect. They're looking for big gains, like maybe 50% reduction in NFT self-heating.
Fighting physics at the nanometer scale with extreme temperatures sounds like a fun job.
Keeps things interesting for sure.
Okay, so let's wrap this up. If you're listening, what are the key things to take away from this deep dive into HAMR?
Okay, first big takeaway. HAMR works. It successfully breaks through that density wall that limited older PMR drives. It does this using that precision laser pulse to temporarily soften the magnetic properties of these super stable iron-platinum materials, making them writable.
Right. Key takeaway, too. This isn't science fiction anymore. It's here now. It's given us 30 terabyte drives already, and there's a clear, believable path to 100 TB and beyond within the next decade or so. This means hard drives will continue to be the backbone for storing massive amounts of data cost-effectively, keeping pace with our exploding data needs.
Exactly. And the third point, AMR is becoming the industry standard. Cloud giants are using it, competitors are adopting it. And it's an important pharisee, but the engineering challenges aren't completely solved. Making that tiny near-field transducer, the NFT, last reliably under extreme stress is still the major focus of ongoing development.
So looking even further ahead, what comes after HMR? Or does HAMR itself keep evolving?
Both, probably. The innovations build on this foundation. People are already talking about things like heat dot magnetic recording or HDMR
Yeah.
that would combine HAMR's heating with another tech called bit patterned media, where the magnetic bits are physically separated on the disk. That could push things beyond 120 TB.
Wow. So layering tech on top of tech.
Yeah, maybe even multi-layer recording. It's this amazing mix of light physics, material science, quantum effects, all working together.
Okay, so here's the final thought to leave you with. Let's assume HAMR delivers on its promise. We get those 100 TB drives, maybe even cheaper per terabyte than today. What does that unlock? What kind of massive new things become possible when storage is that cheap and plentiful? Think about training truly enormous next-gen AI models, or creating global digital archives holding, well, everything, or maybe applications we haven't even dreamed of yet. The future of data storage is quite literally on fire.
Thanks for diving deep with us today.
Yeah, thanks for listening. We'll catch you next time on The Deep Dive.